In this lesson, I'd like to use all the tools that we've discussed in class and solve 3 problems. Here's number 1. Please pause the video now and find all the real zeros of f of x. The first tool I'm going to ask you to use is the rational zero theorem. Now, you can go back and read that in detail, but basically this is the technique we use to list all the rational zeros, all the possible suspects. Now, you'll notice that I'm listing mine in a slightly unusual way. I'm going to put the 25 all the way to the left and negative 25 all the way to the right. I have an idea on how I can narrow down my suspects as I go, so I'm going to more or less put them in numerical order. The next tool I'm going to use is one we've used often in class, and that's synthetic division. It's a very simple way to do polynomial division. I'm going to try positive 5 first. Now, I've just noticed a pattern on the last row of my synthetic division. That is, all the last numbers come out to be non-negative or positive. That means that number is the upper bound. In other words, since the last row is all positive, then 5 is the upper bound. I'm going to go up here and draw a line, and I'm not going to test any numbers greater than 5. I'm going to try negative 1 next, and I think there might be a pattern here also. Notice that it goes positive, negative, alternating signs. This is an example of a lower bound. In other words, on my list of suspects, I'm going to draw a line right here at negative 1, and I'm not going to test any of those numbers below. So my suspect list actually got a lot shorter. Next, I'll try 2.5. With a remainder of 0, I know that 2.5 is a root of this equation. It's a 0 of this polynomial. And one of the factors is x minus 2.5. And then I just write my second factor turns out to be a quadratic. So I'm going to go to work with it. Going to go to work on it rather with the quadratic formula. And it turns out that I'm going to get a negative in the square root, which means this thing has imaginary roots. So if I were to list all the roots of this equation, f of x, I'm going to get positive 2.5, one imaginary root, and another imaginary root. I don't see this kind of thing very often, so I think I'm going to take a look at the graph. And I notice that my graph only hits the x-axis, I think, at one point. I'm going to zoom in on that a little closer. And then when I think I'm close enough, I think I'm going to trace it from here. And I notice that a 0, 2.5, that was in the list that I came up with. So I calculated my root algebraically and used a calculator to verify it. Please pause the video now and find all the real zeros of this equation. The first technique I'm going to apply to this problem is Descartes' rule of signs. That is, I'm going to take the function just as it is, and I'm going to notice how many variations there are in the signs. So let's say I go to positive to positive to positive to positive. Looks like I don't have any changes at all. So as the function originally stands, there are no variations, so there are no positive roots. If I substitute negative x into this function, though, and then check it again, it's negative to positive to negative to positive. Well, that changed 3 times. Now I knew there was going to be 3 complex roots, but it looks like 3 of those roots, all of those roots, are negative. Now I'll make a list of my suspects. Just as I'm sure you found, negative 3 is a 0, so x plus 3 is a factor. That would mean my other factor is x squared plus 3x plus 1, a quadratic. So I'm going to use my quadratic formula to find my last two zeros, which are negative 3 plus radical 5 over 2 and negative 3 minus radical 5 over 2. An approximation of them would be negative 0.38 and negative 2.62, which I think I'd like to check on the graph. Let's see. Looks like there are two zeros here. It looks like it's the x-axis twice. I'm going to zoom. Oh, this is one of those situations that actually hits it twice. So if I trace this, let's see, the 0 on the left is negative 3. So that one I knew. Let me check the other two I'd figured out. One of them I think came out to be negative 2.62. Excellent. That's the second one. And then if I go back, let me see, zoom out again and look at that third one. If I zoom in on that and then trace this, I think that's going to be negative 0.382, and that's the other root that I calculated. This is our third and last problem of this lesson. Please pause the video now. The first theorem I'm going to try to use is Descartes' rule of signs. I count my variations and it looks like I have only one positive root. Then if I substitute in a negative x instead of x, then the number of variations I have is 3. And that makes sense. 3 negative roots. Using the rational root theorem, I'm going to make a list of my possible zeros. I'm going to write them in order here, and I think you probably know why by now. I'm going to grab a number, random here, start with 2. And I'm going to use synthetic division to find out if this is a root. It's not, but my numbers all came out to be positive, my last row, so I know 2 is an upper bound. So I'm not going to try any numbers larger than 2. Now I'll try negative 2, and I find, oh, I got lucky. So x plus 2 is a factor, and negative 2 is a root. So now I know that x plus 2 is a root, which leaves this cubic factor here. I'm going to try 3, or rather 1, and that also turns out to be a 0. So x minus 1 is a factor, and 1 is a root. Let's see, if I wrote this out so far, I'd get x plus 2 times x plus minus 1 times this quadratic factor. And that's another way to write the original function f of x. This is a quadratic. The quadratic factor, I can use the quadratic formula. Simplifying, I'm going to get negative 1 and negative 2. So writing this all out, I'm going to get x plus 2 times x minus 1 times x plus 1 times x plus 2. So negative 2 shows up twice. The zeros here are going to be 1, negative 1, and negative 2, with negative 2 being, I got to look at the graph on this. So if I zoom in on this one point. Where does this thing hit the x-axis? I thought it might be one of those where the graph dips below the x-axis, but it only hits once. So let's see, I knew about 1, and I knew about -1, but I wasn't sure about -2. But -2 also is a 0. It just happens to be a 0 twice. So let's tie this all together now. If I have to find all the zeros of some polynomial, the first thing I'll use is Descartes' rule of signs. I'm going to use that to figure out how many positive and negative roots I have. Once I know that, I'm going to use the rational zero theorem to make a complete list of all the possibilities I have. Then I'm going to use synthetic division on each one. If the last row is all positive numbers, I found an upper bound. If they alternate in signs, I found a lower bound. And using all these tools, I can find the zeros or factors of any polynomial. That's the end of our lesson. Thank you for your time and attention.